Estic molt content de ser aquí. So I really am very happy to be here, and I want to thank the people who helped to get me here, especially Carl, Thomas, Sven, and Chiara. And look, it's going to be a terrific conference. It's a privilege to be here. Over my philosophical career, I've been interested in various topics, but certain topics have especially gripped me, perhaps even obsessed me. They've struck me as somehow being especially important, even foundational. So for a long time, I've obsessed about the nature of conditional probability. I've worried about infinite decision theory, as one finds in Pascal's wager, and how that contaminates even everyday decision-making. I've worried about counterfactuals. I think most of them are false, and I think that has widespread ramifications. Today, I want to share another of my obsessions with you involving regularity. Now, this one might strike you as a little bit odd because it might seem rather small, rather innocuous. And part of my project is to convince you that it is indeed important and even foundational. Now, a handful of you have seen previous outings of this talk. As I say, it's been a sort of long-standing obsession of mine, but I can assure you, you have not seen all of it. In fact, some of what I'll be presenting, I only figured out on the plane coming out here. Well, the topic is regularity, and I'll be discussing its fluctuating fortunes. Here's a first stab at it. If x is possible, then the probability of x is positive. And if you like symbols, here they come. Okay. Diamond x, then P of x is positive. Now, I'll give many reasons to care about regularity. This will explain my obsession. And so it's important to formulate it carefully, and I'll complain that this has not always been done in the literature. I'll look at various formulations of it for subjective probability, some implausible, some more plausible. And I'll offer what I take to be its most plausible version, a constraint that bridges doxastic modality and doxastic, that is, subjective probability. But even that will fail, or so I will argue. There'll be two different ways to violate regularity. There'll be, so to speak, the obvious way, zero probability assignments to genuine possibilities. And then there's the, I think, less obvious way, no probabilities at all, probability gaps to genuine possibilities. And both ways create troubles for pillars of Bayesian orthodoxy. My obsession again, the ratio formula for conditional probability, conditionalization characterized with that formula, the multiplication formula for independence, and expected utility theory. The failure of this seemingly innocuous constraint has ramifications that strike at the heart of probability theory and formal epistemology. All right, away we go. Here it is again. If x is possible, then the probability of x is positive. Now, we already had the probability axiom that said probabilities are always non-negative. And now this constraint gets the tiniest strengthening if x is possible. The inequality becomes strict. P of x is strictly positive if x is possible. And I tell my graduate students, draw diagrams whenever you can. Here's a diagram. Van Fraassen gives us what he calls the muddy Venn diagram as a way of thinking about probability. The idea is that you have a rectangle, you have infinitely divisible mud spread over the rectangle, normalized to 1 unit of total mud, and then the probability of a proposition is just the amount of mud heaped over that region of the Venn diagram. Now, regularity amounts to the constraint there are no bald spots on the diagram. So there's mud, at least a little bit, everywhere. Well, regularity. I find it a staggeringly unmnemonic name, but It's a commonsensical idea. I mean, why regularity? I would call it something more like open-mindedness. Anyway, regularity, that's what Carnap called it, and that's what we call it now. And I think it does capture folk thinking about probability. I think the folk assent to claims like, if it can happen, then it has a chance of happening. In fact, I did an empirical study of this. I did a survey. I asked 2 of my friends, and they agreed, and I thought, okay, that's emphatic confirmation. Regularity's embedded in folk thinking about probability. But never mind the folk. Here are some notable advocates of regularity from the Hall of Fame. Jeffrey, Carnap, Shimoni, Kemeny, Edwards, Lindman, Savage, Stolnacker, Lewis, Skirms, Appiah, Jackson, Hofweber. Okay, they've all advocated some version of regularity. All right, now I want to give you 10 reasons, my top 10 reasons to care about regularity. And I'm inspired here by, some of you will know Dave Letterman with his top 10 lists. In fact, I just checked one of his more recent lists. It was a top 10 reasons, top 10 interesting facts about Donald Trump. Number 10, during sex, Donald Trump cries out his own name. Anyway, I assure you that this top 10 list never will make it on any Dave Letterman list, but it's good enough for us. Number 10. Regularity promises a bridge between modality and probability, a bridge that illuminates both. Okay, so we've got the sort of on-off binary modality, the diamond. We've got the quantitative modality, probability, and now we have a bridge between them. That's interesting. Regularity promises a bridge between probability and truth. So we have, if X has probability 0, then X is impossible by regularity, hence actually false on most understandings of possibility, assuming the T axiom. If X has probability 1, then X is necessary, hence actually true. So we have this nice bridge between probability and what actually happens. Now, people who are fond of Humean supervenience would say, well, you already get probabilities out of the facts, but not everyone will assume Humean supervenience. And then there are precious few bridges between what actually happens and probability. But here's one, if regularity holds, that is. If regularity fails, even this is a bridge too far. Regularity may provide a bridge between traditional epistemology and Bayesian epistemology. For a long time, it seemed like these two traditions were just going on pretty much separate tracks. Now, lately, there's been a lot more engagement between the two kinds of epistemology. But anyway, regularity, as we'll soon see, would immediately give us a nice connection between these two traditions, these two approaches. Regularity promises to illuminate rationality, our topic here. It would provide a much-needed additional constraint on rational credence that goes beyond coherence. Okay? So Bayesians are fond of saying that rationality is all about coherence. Well, it's not just that, and at least this is another constraint. Seemingly minimal, as we'll see, it's too much. Another reason to care, various Bayesian convergence results require regularity. So we're told, in the long run, Bayesian agents will converge to the truth, or different Bayesian agents will converge to agreement. Well, yeah, assuming regularity. If the agent starts off by assigning probability 0 to where the truth is, then they'll never converge there. That's the worry. Regularity would protect against that. Speaking of convergence, regularity would allow us to simplify various so-called probability 1 convergence theorems. For example, the strong law of large numbers. Okay, so the strong law of large numbers says, under suitable assumptions, the relative frequency converges to the true probability with probability 1. And there's that caveat. out the front. It's an almost sure result. But if we could assume regularity, it becomes sure. We can strip away that annoying probabilistic qualification. The thing will just converge, period. Another reason to care, centerpieces of synchronic Bayesian epistemology face problems when regularity fails, and I'll be saying a lot about that a bit later. And the centerpiece of diachronic Bayesian epistemology, conditionalization, faces problems without a version of regularity. Yet it also conflicts with regularity. We have a bit of a dilemma. Bayesian decision theory faces problems if regularity fails. So failures of regularity pose some of the most important problems for probability theory as a representation of uncertainty, and that brings me to the final reason for caring. These failures motivate other representations of uncertainty, Popper functions, ranking functions, non-Archimedean probability, NAP, comparative probabilities, and so on. All right, so they were reasons to care about regularity. I think the stakes are high. I hope I've convinced you that it matters. I mean, they're not sort of war with North Korea high, but by our standards, pretty high. Well, formulating regularity again. This is the schema, but it's just a schema. And as we philosophers know, there are many senses of possibility that could be in the antecedent, many senses of probability in the consequent. So in the antecedent, do we mean logical possibility? Do we mean metaphysical? Do we mean doxastic? Do we mean nomological? Or what? Okay, so this is part of my complaint, that we need to be really careful at this stage. And there are also many senses of probability in the consequent. Are we talking about objective chance? Are we talking about evidential probability? Are we talking about degree of belief? Degree of belief of what? Some idealized agent? Okay, so again, we need to be careful. Now, pair them up, the possibilities in the antecedent, the probabilities in the consequent, and we get many, many regularity conditions. Some are interesting, some are not, some are plausible, some are not. I want to focus on pairings that are definitely interesting and somewhat plausible, at least initially. And in the consequent, let's restrict our attention to rational subjective probabilities. And since our topic here is rationality, that's a good thing. So this will be the schema slightly refined. If X is possible, in a sense that we will soon discuss, C of X, let's make it your credence. You're a rational agent, so from now on, I'll be talking about you and your credence function C. C of X is positive. All right, what about the antecedent? Well, I think here's one stab at it, but it's untenable. Let's call it logical regularity. If X is logically possible, then your credence in X is positive. And Shimoni and Skirms present a version of that. Well, problems. There are all sorts of propositions that are logically possible, but that are a priori knowable to be false and may rationally be assigned credence 0, I say. Obama is a three-place relation. Okay? In some sense, that's logically possible, but I think it's fine to give it probability 0, maybe even required to assign it 0. Clinton is the number 17, ditto. The probability axioms are not themselves logically necessary, so logical regularity curiously would require an agent to give positive credence to their falsehood. All right, so I'm not a big fan of logical regularity. I think this one's more plausible. Let's call it metaphysical regularity. If X is metaphysically possible, then your credence in X is positive. Well, actually, will it be U? We'll soon see that's qualified. In fact, Lewis gives us an important qualification. His 1980, that's the principal paper, the Subjectivist's Guide to Objective Chance paper. Here's his formulation of regularity. C of X is 0 only if X is the empty proposition true at no worlds. And as we know, according to Lewis, X is metaphysically possible if and only if it is true at some world. And Lewis regards regularity in this sense as a constraint on initial, as he says, what we might call prior credence functions of agents as they begin their Bayesian odysseys. Let's call them Bayesian superbabies, okay? So a Bayesian superbaby is born a tabula rasa, but logically omniscient, very smart, and starts conditionalizing as the evidence comes in. But Lewis says superbaby, by the way, Lewis literally used the word superbaby, at least privately. He was a bit of a superbaby himself, I think. Superbaby starts out with this constraint, regularity. Well, still not quite right, I think. A problem for metaphysical regularity is a constraint on superbabies. It's metaphysically possible for no thinking thing to exist. So by regularity, one must assign positive probability to this, to there are no thinking things. But far from being rationally required, this seems to be irrational. Among other things, it leads to a Dutch book argument, the likes of which you've never seen before. So imagine this, you assign positive probability to there being no thinking thing. So you would pay a positive amount for a bet that pays, say, $1 if there are no thinking things. So when exactly do you get to collect? Okay, it's a bet you can't possibly win, but you're prepared to pay money for it. That doesn't seem too good. And anyway, look, it's at least rationally permissible to assign probability 0 to no thinking thing existing, contra metaphysical regularity. However, doxastic possibility seems to be a promising candidate for pairing with subjective probability. And let's call this doxastic regularity. If X is doxastically possible, then your credence in X is positive. Well, what do I mean by doxastically possible? We might think of a doxastic possibility for an agent as, well, something that's compatible with what she believes. And note there the bridge to traditional epistemology that I was promising. Or something that she's not certain is false. Or perhaps some other understanding, and I invite you to plug in your own favorite understanding. And actually, I think it's all to the good that I can be somewhat open about the understanding, because I would claim clearly any such version will fail. I hope my arguments will convince you of that. So just to cover any such understanding, I'll speak of a doxastically live possibility, for short, a live possibility, and I've given you some possible understandings of that, or you might prefer your own. So from now on, I will understand regularity as, if X is a live possibility, then C of X is positive, relativized to U. And as I say, all the better that this can be understood in multiple ways, for I'll argue that on any reasonable understanding of live possibility, it's false. So on any understanding of live possibility, regularity is going to be dead. And this is interesting. If doxastic regularity is violated, then offhand two different attitudes are conflated. So 0 is playing double duty if you have that kind of failure of regularity. You've got, on the one hand, 0 assigned to genuine impossibilities, but then there's also the other kind of 0, where something is a live possibility but still gets the same number. It's as if probability theory's got slightly blurred vision. It can't make certain discriminations, like between the genuine impossibility and the possible but just unlikely case. And the problem's not just at 0, but throughout the entire 0, 1 interval. So take some other value, let's say a half. So let that be the probability that you assign to the fair coin landing heads. But it's also the probability that you assign to that disjoined with one of those 0 cases that are live. So heads or live possibility are also conflated in this sense. They're both getting the same value. Half is doing double duty. We have slightly blurry vision there and everywhere. Doxastic regularity avoids the problems with the previous versions. There's no problem assigning probability 0 to Clinton is the number 17. It's not a live possibility. There's no problem assigning probability 0 to no thinking thing exists. It's not a live possibility. So you're still, that's all compatible with doxastic regularity. And yet doxastic regularity appears to be untenable. If this version of regularity fails, then various other interesting versions will fail too. Let's call this one epistemic regularity. If X is epistemically possible, then your credence in X is positive. This is stronger than doxastic regularity, so if it fails, if doxastic regularity fails, so does this. Or you might like evidential regularity. If X is not ruled out by one's evidence, then credence in X is positive. And so it goes. All right, there will be 2 ways to be irregular. There's, so to speak, the more obvious way. It assigns 0 to some live possibility. And I'm certainly not the first person to be making these points. For example, Tim here has made such a point. Then there's maybe the more surprising way. The probability function fails to assign anything to a live possibility. It just goes gappy. Those who regard regularity as a norm of rationality must insist that all instances of 1 and all instances of 2 are violations of rationality. Right? No zeros, no gaps is the thought. I'll argue there are rational instances of both, zeros and gaps, for live possibilities. So to warm up, let's look at our favorite dart example. It seems every time I give a talk, I throw a dart at random at the 0, 1 interval of the reals. And here's a picture of that. And we make the usual assumptions for this very contrived case. The dart is infinitely thin-tipped. It will land on an exact point, a real number, and it's unbiased. Tension mounts. Here comes the dart throw. Where will it land? Bang. About 0.37. Actually, that was so much fun. Let's do it again. Whoa. Gosh, it keeps on landing on the same point. What are the chances? Anyway. All right. So what you just saw was an event of probability 0, and I mean 0. I don't mean infinitesimal. We'll get to that in a moment. Various non-empty subsets get assigned probability 0. All the singletons. Indeed, all the finite subsets. Indeed, all the countable subsets, like landing on a rational number. And even various uncountable subsets. For example, Cantor's ternary set. Okay. Now that's pretty familiar. Soon we'll get into less familiar territory. Examples like this pose a threat to regularity as a norm of rationality. So put yourself in the shoes of Super Baby, or even your own shoes. Any landing point in 0, 1 is a live possibility for our ideal agent. Okay? Live possibility, probability 0, problem for regularity. All right. So now we're really getting into the arguments against regularity. And the lesson that I draw from this warm-up was in order for P to be regular, there has to be a certain harmony between the cardinalities of P's sample space and its range. If the sample space is too large relative to P, regularity will be violated. So to speak, P just can't keep up. It just doesn't have enough values to assign to stay regular. Kolmogorov's axiomatization requires P to be real valued, and this will be important soon. Kolmogorov says, from now on, forevermore, all probabilities will be real valued. And this means that any uncountable probability space is automatically irregular. I showed that in an earlier paper. Well, it's curious that this axiomatization is restrictive on the range of all probability functions. From now on, evermore, the real numbers in 0, 1, and not a richer set. Okay, so you are stuck with that as your range. Yet it's almost completely permissive about their domains. I mean, Kolmogorov says start with a set, omega, the sample space. It can be any set you like, however large. And then you take a field, a set of subsets that get assigned probabilities. And that can be any field on omega, however large. It could be the power set. Okay? Or, giving this a philosophy of mindy spin, we can apparently make the set of contents of an agent's thoughts as big as we like, but we limit the attitudes that she can bear to those contents. The attitudes can only achieve a certain fineness of grain. So in Kolmogorov's hands, real numbers, and that's that. Put a rich set of contents together with a relatively impoverished set of attitudes, and you violate regularity. All right? So this is going to be one of the main recipes. Okay, at this point, some of you might be itching to reply. Bring on the infinitesimals. So the friend of regularity replies, if you're going to have a rich domain of the probability function, you'd better have a rich range. And here's Lewis, pretty much saying it. You may protest. There are too many alternative possible worlds to permit regularity. I'll interject, yes, I do protest. But that is so only if we suppose, and I want you to mentally highlight those words, but that is so only if we suppose, as I do not, that the values of the function c are restricted to the standard reals. Many propositions must have infinitesimal c values. C. Bernstein and Wattenberg, 1969. All right, and the picture here looks like this. Now, so to speak, squeezed in between 0 and all the positive reals is this whole rich structure of infinitesimals with names like epsilon and epsilon on 2 and so on. Okay, and the Lewisian thought is that if you help yourself to these, you can stay regular. And again, you may protest there are too many alternative possibilities. That's so only if we suppose that the values of the function c are restricted to the standard reals. Many propositions must have infinitesimal c values. C. Bernstein and Wattenberg. Well, I have seen Bernstein and Wattenberg. And their article does not substantiate Lewis's strong claim that there are too many possible worlds to permit regularity only if C's values are restricted to the reals. Okay, so what goes on in that article? Bernstein and Wattenberg show that using infinitesimals, one can give a regular probability assignment to the landing points of our fair dart throw, the one that I started with, okay? Well, that's cool. So far, so good. But that's a very specific case with a specific cardinality. Indeed, Lewis himself thinks that the cardinality of the set of possible worlds is greater than that, at least Beth 2 on one census. But actually, even that seems to be quite an underestimate. We need a similar result that holds if the set of possibilities has higher cardinality than that of the real interval 0, 1. So to speak, we need sort of latter-day Bernstein and Wattenbergs to keep on coming along and keep on assuring us that we can stay regular by some suitable assignment of hyperreals, even when the sets get really big. much bigger than just our initial dart throw. Indeed, the set of doxastic possibilities may well be a proper class. So for an agent, it might well be a live possibility for each cardinality k that there are exactly k things in the universe. Okay? Well, there are proper class many cardinalities. So right there, we've got proper class many live possibilities. Now we're really getting into trouble. But even the trouble starts well before that. So my younger self, and some of you have probably heard me, conjectured that a version of the cardinality problem would always arise. It wasn't just, that special case of the dart throw being too much for Kolmogorov's real valued probabilities. Pruss proved it. If the cardinality of omega is greater than that of the range of P, then regularity fails. Okay? So this is simply a cardinality argument, and in particular, no symmetry assumption is needed. Cardinalities do all the work. But actually, I think there are two main routes to violating regularity. And I've spoken now about the cardinality route, and I like it. But also, there's a symmetry route. If we add a symmetry assumption, we have another, more intuitive argument. We can scotch regularity even for a hyperreal valued probability function, Bernstein and Wattenberg style, by correspondingly enriching the space of possibilities. So here's the dialectic. Kolmogorov came along, all probability functions are real valued, all right? Then along came the dart throw at the 0-1 interval of the reals, and that was too much for the functions to handle, to stay regular. And then along came Lewis, and he said, bring on the hyperreals, see Bernstein and Wattenberg. Okay, two can play this game. It's my turn. I'm going to correspondingly enrich the dartboard. The dart is now thrown at the 0-1 interval of the hyperreals. And let's draw a picture of that. Okay, so this is now the hyperreals, and I want you to fixate on what I've called X. That's a particular hyperreal. We're going to throw a dart, tension mounts. Whoa. How about that? Landed right on X. What's the probability of what you just saw? Okay. The answer's 0, and I really mean 0, and I don't mean infinitesimal. Okay? Here's the argument. X is strictly contained within nested intervals of width epsilon for each infinitesimal epsilon. So you see I've drawn an interval of epsilon width centered on X. And the probability of each interval is its width, epsilon. Now that assumption can actually be somewhat weakened, but let's use it because it just makes the reasoning easier. So the point's probability is bounded above by all these epsilon, and thus it must be smaller than all of them, that is 0, and I really mean 0. Or let me just say it in other words, another way of making the same point. Suppose for reductio that the probability of what you just saw was something positive, some infinitesimal, let's call it, say, delta. All right? Now consider an interval of width, delta divided by 2, covering the point. Okay? The probability of landing in that interval is delta divided by 2, which is smaller than the probability of a point strictly contained within it, violating probability theory. You can't give smaller probability to the bigger set. Hence, we have to reject the assumption of the reductio. The probability of X is not positive delta, it's 0. All right. So things get interesting here. I envisage a kind of arms race. So we scotched regularity for real valued probability functions with sufficiently large domains, uncountable. That was the first dartboard. And then the friends of regularity fought back, Lewis, bring on the infinitesimals, enrich their range, make them hyperreal valued probability functions. Okay, then it's my turn. The enemy of regularity counters by enriching the domain. I made the dartboard hyperreal valued, and so it goes. By Pruss's result, the enemy, me, can always win for anything that looks like Kolmogorov's probability theory. By that I mean where you say, from now on and evermore, probabilities will have this kind of range, real valued or hyperreal valued or whatever, hyper real valued, but you fix in advance what they are. Well, you might say, could we tailor the range of the probability function to the domain for each particular application? Okay, imagine the general of a defense force. He's not sure just how many troops to send out. So he waits and sees how big is the invading force, and then he decides how big to make the troops. The trouble is that in a Kolmogorov-style axiomatization, the commitment to the range of P comes first. Okay, P is real valued, or hyperreal valued, or whatever valued. On the tailoring approach, a probability function is a mapping from F, the field, to, well, to what? Well, I won't tell you. I'll wait and see. That's an interesting axiomatization. And in particular, what will the additivity axiom look like? And it matters. So Kolmogorov told us, forevermore, probability functions are countably additive. Okay, you can't even make sense of that in the hyperreal framework. Okay, you have to use something else, like star additivity. Okay, and so it goes. So what will that additivity axiom look like on the wait and see approach? And in any case, this wait and see approach is quite a departure from Kolmogorov, who did not wait and see. I mean, I'm no fan for other reasons of Kolmogorov's approach. I mean, it's a great achievement, but I think there are all sorts of philosophical problems. And this would be another one on this view, the wait and see view. So, on a Kolmogorov-style approach, there will always be an omega that will have non-empty subsets assigned probability 0. Okay, and at this point we will shift gears. And I promised you a different route to irregularity. And here I'll argue that you can rationally have credence gaps. Starting with good old non-measurable sets. I tell my graduate students, when you can draw a picture, it's surprisingly hard to draw a picture of a non-measurable set. But here's an attempt. All right, so I'm trying to convey the sort of amorphous, non-constructible, nebulous nature of the non-measurable sets, but we know they're in there. Perfect. So certain subsets of omega, so-called non-measurable sets, get no probability assignments whatsoever, given the operative assumptions, the symmetry, given countable additivity, given the axiom of choice. Okay, different kind of case. Let's call them chance gaps. Okay, the principle says roughly the following. Another thing I tell my graduate students is when someone is about to tell you about the principle, start your stopwatch and time how long it takes before they get it wrong. And it normally happens in the first second. And so here we go. The principle says your credence in X, conditional on it having chance X, should be X, and we could symbolize it like that. And if you like, we could throw in some stuff about admissibility. Okay, so that is not what the principle says. I got it wrong in the first second. It's not about you. It's not your credence. It's Superbaby's credence. It's an initial credence. And it actually makes the world of difference, but that's another talk. Anyway, let's go with the rough version. It's good enough for our purposes here. And a relative of the principle would be like this. This is the one for chance gaps. Your credence in X, conditional on it being a chance gap, should be gappy. Okay? So given that the chance of X is undefined, the credence in X is undefined. all right? So the thought here is something like, what business do you have filling in the gap that chance itself can't fill? But anyway, all I need is that rationality sometimes permits your credence to be gappy for a hypothesized chance gap, okay? So you're allowed to inherit the gappiness, so to speak, in your own credence. And there are arguably various examples of chance gaps. Maybe chance statements themselves, claims about chance. Interesting cases of indeterminism without chances. If you know the cases Ehrman's Space Invaders or Norton's Dome, Anthony Eagle has a nice discussion of these, argues that you get chance gaps out of these. All right, now I'm progressively giving you sort of easier to understand, more intuitive examples, but also more controversial. So the non-measurable set cases is sort of hard to get your head around, harder still to draw a picture of, but at least it's rigorous. Okay, now let's go to the other end where perfectly familiar, perfectly straightforward example, more controversial, one's own free choices. And in particular, Kuyber, Gilboa, Spohn, Levi, Briggs, Liu, Price contend that when I'm making a choice, I must regard it as free. In doing so, I cannot assign probabilities to my acting in one way rather than another, even though onlookers may be able to do so. Okay, I am deliberating, will I have the white wine or the red wine? And while I'm in the thick of this decision, I cannot, they say, rationally assign credences to white or red, as it might be 50-50. Nothing. As they say, deliberation crowds out prediction. I don't like that slogan. It's more like deliberation crowds out probability, credence. Now, to be sure, these cases of probability gaps are controversial, but these authors are committed to there being credence gaps and thus violations of regularity. But all I need is that it's permissible for them to be credence gaps, and those will be the counterexamples. Okay, and now we're on the home stretch. I've argued for two kinds of counterexamples to regularity: rational assignments of zero credences and rational credence gaps for doxastic possibilities. And I now want to explore some of the unwelcome consequences these failures of regularity have for traditional Bayesian epistemology and decision theory. And back to my old obsession, the ratio analysis of conditional probability, we all know it, and we all know the proviso. You can't divide by zero. So the condition has to have positive probability. Well, what if it doesn't? What's the probability that the dart lands on a half, given that it lands on a half? And this is not meant to be some trick question. We all know in our hearts the answer, right? It's 1. But the ratio formula cannot deliver that result because the probability that the dart lands on a half is 0. You can't divide by 0. Gaps create similar problems. So take your favorite probability gap, G. Yeah, maybe it's the non-measurable set case. Maybe it's I will choose the white wine. Okay, that's G. The probability of G given G is 1. Even when you're deliberating about the wine, you know damn well the probability of I take the white wine given I take the white wine is 1. But the ratio formula cannot deliver that result because P of G is undefined. You get question mark divided by question mark. So I say we need a more sophisticated account of conditional probability, and I advocate taking conditional probability as primitive in the style of Popper and Rennie. Now these become problems for conditionalization, which is defined in terms of the ratio formula, and you know the formula. Suppose the agent learns evidence E, the new probabilities are the old conditional probabilities, conditional on E, and there's that annoying proviso again. The probabilities have to be positive. And what if they're not? Suppose you learn that the dart lands on a half. What should be your new probability that the dart lands on a half? Again, it's not a trick question. You know the answer. but you won't get it using conditionalization so defined. All right. Gaps create similar problems. Suppose you learn that G. What should be your new probability for G? You know the answer. But P old of G given G is undefined, so conditionalization cannot give you this advice, so defined. I say we need a more sophisticated account of conditionalization. Again, primitive conditional probabilities to the rescue. Okay, problems for independence. Okay, this is one of the cornerstones of probability theory, right? Okay, this is where probability theory goes beyond measure theory. Independence has this peculiarly probabilistic character. And we want to capture the idea of A being probabilistically uninformative about B, and you all know the formula, and every textbook tells you A and B are said to be independent just in case you have this nice multiplication of the probabilities. So according to this account of probabilistic independence, anything with probability 0 is independent of itself. Just do the maths. If P of X is 0, then you get 0 on both sides of the independence formula. So independence holds. I mean, I find this scandalous. It's funny, you see the same textbooks, you know, with a straight face telling you on the one hand, probability 0 things can happen, you know, law of large numbers or whatever, and then, probabilistically qualified, and then, here's the formula for independence. Well, I don't know about you, I find this just a clear counterexample. It's not a close call. Identity is the ultimate case of probabilistic dependence. The thing we were trying to analyze was independence of a certain kind. Suppose you're wondering whether the dart landed on a half. Nothing could be more informative than your learning the dart landed on a half. Like, say you've got $1 million resting on this. Does it come as good news when you learn the dart landed on a half? And that's what you bet on. Please don't tell me that that was completely uninformative. But that's what the formula says. According to this account of independence, the dart landing on a half is independent of the dart landing on a half. I mean, that's just a counterexample as far as I'm concerned. And gaps create similar problems. You're wondering whether G, nothing could be more informative than your learning G. But there's no verdict from this account of independence. You have undefined on the left, undefined on the right. We need a more sophisticated account of independence, for example, using primitive conditional probabilities. And Brandon Feidelson and I have been working on this. And this is the very last case, and then I'm done. Arguably, the two most important foundations of decision theory are the notion of expected utility and dominance reasoning. And yet probability 0 propositions apparently show that expected utility theory and dominance reasoning can give conflicting verdicts. Suppose that two options yield the same utility except on a proposition of probability 0. But if that proposition is true, option 1 is far superior to option 2. Okay, two options. 1, if the dart lands on a half, you get $1 million, otherwise you get nothing. Option 2, you get nothing. Which do you prefer? Now, I'm glad you laughed because I hope that was the laughter of the answer is obvious. I say that intuition tells us, indeed yells at us, you should prefer option 1, and I'll say it. Dominance reasoning says option 1 is strictly better than option 2. Expected utility theory says they're the same. Which is it to be? Option 1's better. I think this is a counterexample to expected utility theory as it's usually interpreted. And that's true for both evidential and causal, if you care about that. Now, to be sure, there are replies. They may even come up, but that's the first pass at the argument. And gaps create similar problems. Here are your options. 1, if G, you get $1 million, otherwise you get nothing. Option 2, You get nothing. Come on. Oh, interesting. Whoa, it suddenly takes over. All right, back you go. Expected utility theory goes silent. I say that option 1 is better. So do you, I hope. We need a more sophisticated decision theory. All right. So it's time I wrapped up. Irregularity makes things go bad for the orthodox Bayesian. That's a reason to insist on regularity. And you can see why, remember the Hall of Fame? All of these people wanted regularity. The trouble is that regularity appears to be untenable. I focused on doxastic regularity, but other interesting regularities will meet similar downfalls. Just rehearse those arguments. Just consider again dartboards and so on. I think then that irregularity is a reason for the orthodox Bayesian to become unorthodox. And I've advocated replacing the orthodox theory of conditional probability, conditionalization, independence, with alternatives based on Popper-Renyi functions. Expected utility theory appears to be similarly in need of revision. And apologies to the handful of you who've seen the talk before, but I will end with the same joke. And then there are some possibilities that really should be assigned 0 probability. And for those who have not seen this before, I'll buy a beer to the first person who can identify who this is. Thanks very much.
Thanks. So I was wondering how important the details are of these cases, like the Dart case, because I don't think it's compatible with what I believe, that there are any infinitely fine darts or for other similar versions of the cases. So those cases don't get me very worried because I don't think these are actual doxastic possibilities.
Uh-huh.
And then I guess the more general question behind that is, I guess I have some remaining optimism for the wait and see approach, at least when it comes to real life applications of doing Bayesian epistemology and expected value theory, because I know some things about the world I live in, which is that it doesn't contain infinitely fine darts, and so it seems like, all right, I've got my space, and it's not any of these lovely fancy spaces you described, so can I go ahead and use traditional Bayesian epistemology?
Mm-hmm. Okay, thanks. Okay, several things to say. Actually, I think we have a nice sort of choice point here. We could either, so to speak, highly idealize, and Bayesians often do that, super baby, logically omniscient, and so on, okay? And then I do think that the Dart is fair game. I mean, if we're playing this sort of idealization game, then don't begrudge me the idealization of the dartboard, and we could imagine that the ideal agent can somehow discriminate all the possible landing spots. That was the one fork in the road. The other one would be, all right, then don't idealize so much. Let's really talk more about us, or agents rather like us, maybe slightly improved versions of us. Then I think you'll have irregularity in spades, because we will have all sorts of gaps for things. I was imagining, so to speak, the harder case for at least the gap style of argument, where super baby fills in all the gaps. Well, I argued, no, not even super baby does. But if it's agents more like people, then sure, there'll be gaps all over the place. I won't need to get fancy with non-measurable sets and so on. We'll have them all over the place. And even in the real world, you might say, well, okay, the tip of the dart isn't so precise, isn't so fine, but maybe something else is, like, say, the center of gravity of the dart. You might say that is a point, and I can still entertain propositions about that. All right, next part of my answer is that's all fair enough about the 0 cases, but then there's also, remember, the other route to irregularity, like the gaps. And and we could have another version of this conversation about them. Again, the non-measurable sets, I'm sure you'd say, well, they're sort of far-fetched and you don't have to worry about them in the real world. Will I have white wine or red wine for dinner? That's very realistic. It's more controversial as a case of a gap, but I did want to throw it in. Okay, and then finally, you said maybe we should adopt the wait and see approach. And maybe we should, although notice we are not doing Kolmogorov anymore, and that's big news, okay? Because we were told, hey folks, Bayesians obey these axioms, and the axioms begin by saying forevermore probabilities will be real valued. If we are abandoning that, then let's be clear about that. You know, the rules have changed.
Thanks, Alan. So ultimately, I wouldn't want to defend regularity, but let me play the devil's advocate a little bit at least. So I thought there were two parts of your talk where you were, at the very least, a bit too quick for me. One was where you relatively quickly dismissed this version, if x is logically possible, then the rational credence for x is greater than 0.
If x
is logically possible,
yes, right.
Yeah.
Yep.
So that, like the Skirms and other people have.
Yep.
So the three examples that you had, they didn't quite convince me. So the first example was, right, don't we know a priori that Obama couldn't be a ternary relation, right? I don't know. Who knows, right? You know, I'm not in metaphysics, you know, that much. But if I remember correctly, there are views like you couldn't distinguish properly, in any substantial sense, between universals and substances. Like I think Ramsey had a view a bit like that. So who knows? Maybe he is a relation. Why ternary? I don't know. I didn't Peirce have a view where there's something special about ternary relations? You know. So there you are. Okay, and these are reasonable people. So you see. Maybe we should have leave that open on the credence side. Similarly, for Obama equals 17, was it?
Or Clinton.
Or 13 or something like
Obama
that.
Will do.
Right. Remember, there's the Julius Caesar problem in the philosophy of mathematics, where people are thinking, well, maybe we get a grasp of natural numbers via abstraction principles. Yeah. But then these abstraction principles don't tell us exactly what these objects, like number 13 or 17, are. Maybe they are, one of them is identical to Julius Caesar, who knows? And it could well be that's the only thing that we will ever know. That's what's given by the abstraction principle, and we never can rule out that, 17 is one of these physical entities. Yeah. So maybe we should, invest a little bit of credence in that option too, and not rule it out a priori too quickly. And finally, wouldn't they have to assign then to the probability axioms probability 0, because these are not logical truths? Maybe you need a slightly more tolerant notion of logical truth. Think of doxastic logic, right? Yeah. There are logical truths involving the be operator, the belief operator, all of a sudden, right? Introspection maybe, consistency of belief. And you could think of that in the same way, and then the axioms of probability would themselves count as logical principles. And so, you wouldn't, it would be fine to, they wouldn't be considered a counterexample, I think, yeah. So that's one thing. And the other thing was, I'm also a fan of the wait and see strategy, the dialectic. And the reason is, I think of what we are doing when it's about rational credence is it's an episode of rational reconstruction or explication or so in the Carnapian sense, okay? So I do think we start with something like the real people's degrees of belief, but then we clean them up and systematize them and make them more rational and improve them. And then we come up as one option with subjective probabilities. Mm-hmm. So we always start with sort of the thing there, with the army invading, and then we cook up our explication or rational reconstruction. Yep. And this is the only thing that's demanded is that this is sufficiently similar for the purposes in question. It doesn't have to be a perfect copy. So you can fill in gaps, all of that. If that serves your philosophical purposes, then that's fine. It's also not a claim that there is a uniquely determined or a final way of doing that. So, you can build up a rational reconstruction of actual degrees of belief as subjective probabilities that map to the real numbers, and then you improve by using non-standard reals, and then you improve. Mm-hmm. And that could go on forever. I think that's pretty much exactly what we are doing in formal epistemology. I wasn't convinced that sort of pointing to Kolmogorov and his authority helps here as an argument against what I've just pointed out. I mean, Kolmogorov is great, right? But his axiomatization also served a purpose, and that purpose was a purpose, I think, within mathematics. So, of course, he used the real numbers, right? He wanted to have, for example, something that you could use in the foundations for integration or measurement theory, measure theory, I should say. That you use the real numbers. You're a mathematician. But that doesn't mean that will be the right axioms in our rational reconstruction of, rational degrees of belief or so. I don't think he wanted to cover that territory. And when you pointed to sigma additivity, I think it works against you, I think. Because he included sigma additivity, but I think most Bayesians would not include sigma additivity as an axiom for rational degrees of belief. So why did he include it? Well, because you need it, for example, for integration. But for different purposes, like the rational reconstruction of degrees of belief, it's not a good idea to include it. So this, if anything, undermines his authority, I think.
Thanks. So heaps in there. I'll try to respond to everything, and I've been keeping track. So, I mean, they were good points about maybe I was too fast with the Obama case and the Clinton case and so on. I'd like to think a bit more about the problems you raised, Julius Caesar and so on. At best, that'll only postpone the trouble, right? So maybe I just fast forward to the no thinking thing exists example. It's logically possible that no thinking thing exists.
I just thought the same kind of move could be made, right? We could cite people in the history of philosophy who have said, oh, intelligent, reasonable people for whom thing, substance, lots of questions to be raised about that.
Okay. Anyway. A thing is a maybe philosophically loaded notion, so one should be a little bit open-minded about that after all. Okay. So I guess you're pushing me to just get to the dart a bit faster, because it is logically possible by any reasonable standard of logic that the dart lands, on this given point, and then I finally get my counterexample, I hope. But I thank you for these worries about the earlier arguments. That probably covers the first set of worries you had, and then the second was you like the wait and see approach and rational reconstruction and good old Carnap and all of that. And I had several thoughts. So I also, your points are well taken about Kolmogorov, but remember, Bayesian epistemology typically takes Kolmogorov as gospel. That's the way we do our epistemology. We start with Kolmogorov's axioms. On this wait and see approach, we should stop saying that, okay? We will not be following Kolmogorov orthodoxy. We're going to do this other thing. Wait and see. Well, that's right, but that's not what the Bayesian epistemologists told us. Yeah. So this is a new kind, maybe this is a better kind of Bayesian epistemology. Wait and see Bayesian epistemology, but it's not orthodoxy, and that was one of my main points. And so in that sense, we're agreeing, because remember, my final slides were, let's jettison Bayesian orthodoxy. This is certainly doing that. And even there, you had lots of good comments. You raised a worry about additivity, so I want to respond a bit to that. You said that for modeling agents, one should actually not assume sigma additivity, and I assume you meant just stay with finite additivity. Was that the thought? There are worries there too, like, the nice limit theorems, some of them certainly depend on countable additivity, so you won't be able to help yourself to those. And then there are issues of so-called non-conglomerability, when I'm sure you know what I'm talking about. So roughly, if conditional on every cell in a partition, your probability has a certain value, then unconditionally it should have that value. And think of the reflection principle, okay? If you know in advance that whatever you learn, your probability is going to have a certain value, then have that value straight away. What are you waiting for? Okay, that seems pretty compelling. There'll be failures of that if you only have finite additivity. There'll be non-conglomerable probability functions that'll have this weird mismatch between conditionals and unconditional probability.
But there are quite a few Bayesians who would still reject signal additivity for,
Quite so.
for example, problems with the Dutch dividing.
Yeah, that's right. Yeah, certainly it's a good debate, arguments on both sides, but it's not completely over that the finite additivity folks have won. And then finally, there's still the worry about gaps. And your questions didn't worry about that, and that's fine. But that's another route to irregularity. Okay.
Yep, this is just a minor comment about the first reason you gave for being interested in regularity, because it's a bridge between probability and modality. I mean, it's not that if you reject regularity, you have no bridge, because you've still got the converse of regularity, that a positive probability implies possibility, which, is a non-trivial principle because it requires, as it were, some kind of coordination. Yeah. And it seems to me a better way of putting it would be that what regularity gives you is that the relevant modal notions are actually reducible to probabilistic notions, because you've got a biconditional. Yeah. Whereas if you reject regularity, you lose the reduction, even though you do get some kind of one-way bridge.
Yeah. Okay, spot on. I just completely agree. That's right. It is true that regularity provides a bridge, as I said, but as you've said correctly, the converse already provides the bridge. And there's a better way of selling regularity. How nice if you could get the reduction, which you only get as a biconditional with regularity coupled with the second axiom of probability. Yep, so that's great, thanks.
Just a small point, if you want to avoid the Dart case because it provokes concerns among people, you can just have the example that, if one believes at all that there's some sort of true physical theory for this world, and if you believe in the continuity of space or the solution space for the right physical theory, then the actual world displays some current state in whatever that state space is, and it's going to have measure zero, and so it has to have, but you don't want to assign it, or do you? Probability zero. So that's like the real world Dart is the existence of some actual state for the world now.
Good, that's right, and that's not far-fetched. That's our problem that we face. Yeah, okay, that's good, thanks.
Well, then it's time to thank Alan for a lively talk. Thank you very much.